the Auckland Structural Group presentation this evening. Like the chair has said, I'm Kingsley. I finished from University of Auckland about 2 years ago. And the reason why I decided to do something different from about 90 to 98% of the students here at Auckland Uni, they do their research on seismic design and activity people here as well, which we studied almost the same time. I was a bit curious, why we all do seismic design. I mean, obviously we have earthquake in New Zealand, but then what about the other things which are affecting the buildings, such as fire and wind? And that was the reason why I chose the path of being not a fire engineer, but going into fire engineering and also structural engineering. And through the course of my study, I think got a few questions from a lot of people in terms of, how do we design fire here in New Zealand or in Australasia? New Zealand and Australia almost use the same design patterns. And I've discovered that the majority of the fire engineering design is based on prescriptive design and not performance-based design. And as we all know, we can attest to it, prescription-based design basically is ticking the boxes, just like doing your ISAs, whereby performance-based design is more of using an alternative solution whereby you could actually engineer your building. And this is the reason why I decided to give this presentation. So like the note says, misconception and implementation of fire strategy. So structural design of buildings. Now I guess majority of us here, we are all structural engineers, but we might have a few fire engineers as well. And the first part of this presentation will talk about, basically talk about fire engineering, what's fire engineering, how did it start here, what did we do, and the second part will be more about how this fire affects our structures. Status of fire engineering in New Zealand currently. So we're about 2 to 3 decades behind earthquake engineering. And what's the reason? The majority of the people who do research here in New Zealand, they tend to go into the space of earthquake engineering, and just a handful, I think about 2 or 3 people currently doing the doctorate in something related to fire. And this is why we're still way behind compared to other countries. I was opportune to visit and to attend the conference in 2017. That's the Application of Structures in Fire conference in Manchester, United Kingdom. And just 2 people from the whole of Southern Hemisphere actually attended that conference. So that's to tell you how we don't actually put much effort into structures in fire. And also, there's still some uncertainties in terms of the way fire behaves or the way structures behave when they are subjected to fire loads. And also fire models are currently debated in the sense that because we're still not at the level where we're at with seismic design, people still tend to have different views on how building or structures should be designed in terms of fire. And also, the structural response to fire is largely unknown. Majority of what we know is the elements and not the full structure. Basically, we have the steel frame with composite floor, only system reasonable well. So basically, for the composite floor, we know how the system reacts, but how the components react, but not the entire structure itself. Same thing with concrete buildings and multi-story timber buildings. So just before I start, because the team says misconception, I'll play. This is one funny video which I found online. And this is basically the general misconceptions we have about structures and fire. So this is a footbridge. It's a timber footbridge. And we can see the whole bridge is actually on fire. But what are the chances of that happening? It is happening. So we just watch a little clip, and I'll explain at the end of the video. So the firefighters are actually there, and so this is what we have in mind. But once there is a fire, the whole building comes down all at the same time, and that's the general, misconception we have as either structural engineers or fire engineers. But in reality, this is what we actually have. Okay, so this is basically a warehouse with different fire cells, And what happens if there is a fire in the first fire cell, okay, until you've lost your stability requirements and integrity requirement, insulation requirement before the fire gets to the next fire cell and the next fire cell. It doesn't happen all at once. And this is why when we design, we should start trying to think about the building itself and not just ticking boxes based on prescriptive-based design. So that's what really happens in a fire, not the previous. The previous could happen, but not in a building where you have a separate fire cell, like we generally have here in New Zealand. So this, I'll just start based on the New Zealand Building Act. So the Building Act basically is what holds us as professionals. This is where we tend to go to if there is either a dispute in our design or if we have issues, we go to the Act, which basically supersedes every other thing. And the clause B1, structural engineers design to, and clause C1 to C6, which fire engineers design to, they're almost interwoven. But clause C6 is almost the same with clause B1. And why is that the case? Clause B1 3.3 basically says account shall be taken of any condition likely to affect the stability of building elements, and cite what including, you can see the one in red, fire. Okay, it lists the rest, but fire is actually there. And clause C1, C6.1 says the building must maintain structural stability. Now, with structural engineers, we don't sign clause C6, but we sign clause B1. Now, whose job is it to make sure the building actually stays stable during a fire? Is it a C6 or is it a B1? Anyone? B1. Well, you can see C6 says the building must maintain structural stability. So, why? Who's not sure? Okay. Now, if you go into basically a fire engineering forum, they say, "Oh yeah, it's there in our clause C6. We should sign it." You know. But then that's where you get the overlap. So most of the times you see buildings which are basically prescriptive based and not performance based. It's hard to tell who's meant to sign, you know, clause C6, but we sign B1, which covers fire as well. And a bit about fire engineering, like I said. So in fire engineering, there are two main documents which are being used to design buildings here in New Zealand in terms of fire. So the first is called the acceptable solutions, and that's where you get your clause C1 to C6, and the verification method. So think about an ISA, okay? An ISA is almost similar to your acceptable solutions, all right? You have different criteria you need to meet, and at the end, you get the results, okay? You can see your verification method as a DSA. You still follow those requirements, but it's a much detailed design. So majority of the buildings, for instance, your residential housing, some of the most warehouses as well, depends on the height, and also your regular apartments, most of the fire engineers would tend to lean towards the C1 to C6 or the acceptable solutions. And why is that the case? Now, when you see, for instance, if you have an ISA or a DSA and you get a client, obviously you want to get an ISA for the fee of a DSA, which is easier for you to do. And that's the main reason. Because if you go in with the verification method, you have much rigorous things to do in terms of you need to get a fire engineering brief, you need to speak to council, you need to get information also from the fire service, which is now they call them now?
Fence.
Which one?
Fence.
Fencing, exactly. Fire engineering New Zealand, thank you. Not fire service anymore. So these are the people you go to when you do your verification method. Well, acceptable solution, anyone. Well, basically anyone can sign it. And that's the reason why majority of the buildings are not being coordinated, or during the coordination process, we don't speak to the fire engineers. We structural engineers tend to do what we do without talking to the fire engineers, and that's because the majority of what they do is based on the acceptable solution. Now, this is where today's discussion would link towards. That's the alternative design. Now, what is alternative design? Now, this is where the C1 gets interwoven, the C6 gets interwoven with the B1. So that's where you engineer your building as structural engineer and a fire engineer at the same time. Okay? And this is where we're hoping in the future we get into the space, which is called the performance-based design. So how do we carry out the performance-based design? Now, like it says, it's not 100% compliant with the verification method or the acceptable solution, which means when you get a council with acceptable solution or verification method, you're sure you're going to get your consent. But with the alternative solution, that's a different ballgame because they need to get a rigorous peer review process, and also it goes through various iterations. And in terms of cost, my opinion would be the alternative design will be cheaper for the client, but the acceptable solution will be cheaper for the company. Why? ISA, DSA, which is faster. I'd rather do an ISA, get the money, than doing a DSA. But then when you want to look at the building itself, if you go into alternative design, you're going to engineer the building from first principle, rather than having to use a prescriptive-based design. Please feel free to ask questions during, if you feel you're not following, happy to answer as I go. Now, what is fire? Okay, for there to be fire in anywhere in the world, any location at all, three things need to be there, or three things need to be present. You need to have heat, you need to have oxygen, you need to have fuel. All right, now fuel is not your regular PMS. Fuel could be anything. It could be a piece of paper, it could be firewood. Okay, without the heat, there is no source of ignition. There is no way the fire is going to start. And that is why, without these three components, we need to make sure during our design we check if one of these three are absent. No matter where the building is or no matter what it is, you're not going to have a fire in that building. And the question now is, when you design, for instance, your building and you have a stair or you have a stairs, all right? Now, in general, do we keep materials free, say, under the staircase or in a stairs location? Anyone, do we do things like that? No. So why do we fire it? Or why do we require to fire it? Or why are we required to do it? It's an exit, but there is no fire. There's no fuel.
Depends which way you're fire rating from.
Okay.
It's not an internal fire, it's external fire protecting.
So it's an external stair.
Protecting the pressure.
Okay. So what I'm getting at is, I've seen buildings whereby the acceptable solution says you need to, well, basically, every supporting element needs to be fire rated. So if you have a floor rated for 30 minutes, the supporting element, which is a column or a beam, has to be fire rated for the same amount of fire rating you have for the member it's supporting. But sometimes those members are actually outside the building. So do you still go ahead to fire rating on the members outside because it's supporting a particular floor? That's where acceptable solutions comes into play when you talk about alternative design or CVM2 or verification method. So anyway, that was just a bit of things I've seen out there majority of the times. Places where we don't have fire load or we don't have fuel, they often get fire rated, and I don't know how you could justify that, to be honest. But again, we are not the one paying the bills, so that's good. Fire growth. Okay, so think of a piece of cigarette, okay, or a lighter or whatever. If you light a match and you burn a piece of paper, okay, it's different from having a fire in a building. And that's because there are different stages of the fire growth. Excuse me. So the first stage of a fire is where you have an accident. Obviously, no one wants to burn any building down except it's arson. It's an accident, something happens, and the fire gets lit. And the next is the ignition stage and spreads up to this flashover stage. So the point which we are more interested in is called that flashover stage. And that's where the fire is hard to control. So take, for instance, you burn a piece of matches, okay? It's not going to get to the flashover stage because there is not enough fuel or there might not be enough oxygen to get to that particular level. So by the time we get to the flashover stage, the fire would be almost uncontrollable. It's going to be very difficult for us to control the fire, and that's why we need to get the fire service in, and that's where we start getting our members getting to their limiting temperatures and things like that happening. But looking at the curve, In majority of the cases, when you have a sprinkler system, okay, because the sprinklers have been, but the majority of them have been triggered by the heat in the room or wherever they're located, before it gets to the flashover stage, your sprinklers would have been activated. And that's why majority of the time, the fire doesn't grow to an extent when you have a sprinkler in the building, whereby it's going to be uncontrollable. And you can see the curve, the dashed curve, which is the curve for a fire having a sprinkler system. So this is a video again showing how fast, okay, it takes a few minutes for a small fire starting from a piece of bucket or something to generate into a very uncontrollable fire. Sorry, I'll play the video. So this is an experiment basically trying to see how fast it's going to take for it to generate into an uncontrollable fire. And they just lit a little piece basket and it keeps burning. Just push this a little bit. Okay, and now it gets to the blanket. So this is a full room. And it keeps going. And there you go. And that's where it gets to. Less than about 5-6 minutes, it gets to a full fire, which they cannot actually control. And this is what really happens in a real fire. It starts from little, and that's where you get a flashover stage. All your windows starts to break. Why? Because it needs more oxygen. Because with oxygen, you get more fire in your building. And that's all about fire engineering. So now the next stage, or the next part of the slide, we'll talk more about how this affects our structural elements. So, multi-story building response to severe fire. So these are what we know currently, all right? So for steel buildings, a lot of data and key points are the performance of the system are different to that of the individual members, which I said earlier on, all right? So what we usually do in most cases, we analyze individual members without looking at the global structure. And that way, we don't often know how the whole system works as one, not just individual elements, which is what we know currently. The fire resistance of the system is typically higher than that of the individual members. All right, so if your beam has been designed using 3404 and rated for, say, 30 minutes, the system might be about 40 minutes or 60 minutes in any case. All right, but how do we do that? We need to do more analysis. We need to get information from the fire engineers, from, like, for instance, we need to know what the fire load is. Okay, we don't just look at a fire, a small piece of a room with a fire. Inelastic response will occur in fully developed fires as well. And the detailing, okay, is important with unprotected beams. So I'll talk more about this one. This has to do with your connections and how it's being actually detailed for a fire. Steel columns. How do they behave in fire? What do we know? How do we get the information? So the gravity load and wind load, definitely you have that during the fire. Okay, not too many times you get both a seismic event and a fire event at the same time. So, but there will be always gravity loads there, and there will be wind. So during fire, what happens is the column heats up. This is for structural steel, and it expands. So once the fire expands, you'll see the floor above starts to jack up. So basically what you're doing is you're having a fire in a column, and this column starts to jack the floor above, and the column starts to expand because it still has, and what happens is the axial load starts to increase gradually. And also the restraint of this expansion increases column's compression load, which means once it starts to expand, you get a higher compression load in the columns. And the effects of the column depend on one. So if the column is very strong and stiff, the floor, it jacks up the floor. But if it's not strong enough, what happens is it just squashes or it buckles. So those are the two things that could happen. And that depends, one, on how the column is being restrained, or if the temperature is high enough to actually expand the column. And also the rate of expansion varies based on the temperature reading you're having in that particular room. So these are what we know. So this is a test. This is a very famous test done in this Caddington fire down in the UK. So these are slender columns. What happens is the slender columns, remember, they actually buckle. I'll get a much clearer picture of the next slide. But for stocky columns, what we noticed, or what's usually the case, is at the top, you actually see local buckling of the particular column. Okay, so the column tries to expand, and once it expands, once it gets to the capacity, it drops, and also that the top part of it gets, that's where we get the local buckling of the actual columns. So what about the behavior of braised steel systems? So the same way we have our members when we design for seismic or when we design for earthquake, we have our EBF and CBF. So what happens to the EBFs or the CBFs in the fire? Okay. Now remember, majority of these members, they've been designed to take our lateral loads, which means the gravity loads in this system would be minimal. And in most cases, the take home would be we can actually leave them unprotected. Okay? And the way we do that, it's 3404. I think there is a calculation on the limiting temperature, and once we get the limiting temperature of the members, we could actually design the members and get the fire resistance or structural, the PSA of the members, which is the adequacy or structural adequacy of the particular member in a fire. Also, sometimes, due to the different bays we would have a fire cell or would have the members in two different fire cells. So which means if you have a fire cell, okay, a fire cell is basically a room which has been fire rated all around and at the top, which means if it's fire rated for 60 minutes, the structure or the members blocking the fire wouldn't collapse till after 60 minutes. So if you have a bay and you have a wall which has been rated for 60 minutes, it means if there's a fire here, the other one would actually stay for more than 60 minutes. So when you have a bay or you have the EBFs in one bay with different fire cells, you could actually leave them unprotected. And what about the steel beams? Okay, so we know during the fire load as well, we have the wind, we have the gravity. And during fire, the temperature gradient causes the beams to sag. Okay, so for most of us who've done a few things on the slab panel method, we see a lot of deformation of the beam, and that's due to the fire as well. And during fire, there's an increase in temperature in the beams, and what happens is at the supports, the beam starts to expand at the support, but at the mid-span, it buckles in or it deflects very much, which is very visible. And this is the same photo from the Caddington fire in the UK as well. So 2FX tends to minimize the expansion of the column from beam, but the rotation demands, okay, and the connections, okay, gets higher in terms of when you get your, at the supports, they start to expand and they start to twist. And that way, your rotational demand, which means the connection itself has to be well detailed. And this is why I talked about the connection itself. So behavior of steel frame connections, like I said, during the heating phase as well, the connection are subjected to negative rotation and minor to the axial compression. So once the you have your beam column joint, once the beam starts to expand, it puts a lot of tension in your actual connections. And this is why the detailing of the connection or the rotational detailing for the connection has to be well detailed. But the good thing is the detailing we currently use for seismic detailing for rotations in columns, they actually are sufficient for the fire designs of these actual members. The connection with no inelastic reverse strength in fire must be avoided. Now, it's going to be catastrophic if your beam column joints fail in a fire. That's one of the worst case scenarios that could happen in a fire event. So this is what it looks like. Okay, so we can see we already lost two of the connections due to the fire. But what happens is once it cools off, okay, it starts to contract, and that's where you get even much issues, because now once it starts, getting back to its original state, it tries to put much pressure on the supporting member, and then most of the times you get your connection or your bolts, you lose about 2 or 3 bolts. out of your, for instance, 4 bolts connecting the 2 members. So first of all, the rotational requirement for ductile response in earthquake, like I said, are suitable for fire. And also we can get some design materials using the CNZ report 14. Excuse me. So what about the floor systems? How do they behave in a fire event? So majority of the tests that's been done are usually on composite floors. And the critical direction of fire of the floor system is usually underneath. So this is why in fire engineering, when you fire a member, you go from, the underside of the member. So if, for instance, this is a fire cell, all right? What we need to do, we need to make sure we fire it the underside of the particular floor. Not all floor systems are potentially capable of this behavior, okay? For most concrete floors, most composite floors, we understand the behaviors, but there are some particular floors which are actually questionable. And I'll get to that in the next few slides. So for a composite floor, shows good inelastic behavior, okay? We can see the floor didn't fail, the beams just sagged, and those beams are all unprotected. That's exactly what happened in the experiment. But we can see at the top here, left-hand corner, okay, we can see the major cracks in the floor. Now, think about it. If this were to be, for instance, say, an apartment, and that's your kitchen, okay? And probably your neighbor had a fire or something, and you come and walk in your kitchen and you see, your floor sagging in such a way. Obviously, you're not going to be happy about that. And this is one of the reasons why during your detailing, at the location where you have the columns, okay, we need to have some extra tension members basically to help in the support so we don't have this kind of puncturing shear we're having in that location. So a better detail would look like this, okay? So when we have the bars, and that's why we have the minimum cover during the design, and also the number of bars, I think HG12 is the minimum, you put in your floor to make sure you get that tensile capacity, which would be increased due to fire. Your tensile demand would be increased, sorry. Unprotected still behavior in severe fire. So we've understood, or we try to understand how these sections behave in serious fire. First of all, exposed steel elements may reach close to the temperature of the surrounding gases. So usually, if the room is about 1200 degrees, the unprotected steel would be about 0.95 times whatever the gas temperature is. So this is just a kind of an estimate to know what temperature you're going to be getting. The beams will always sag downwards, okay? That's what happens. The columns would always undergo, axial expansion, but once it gets to its ultimate state, it actually squashes, or you could get local buckling, depends on how it's been restrained. The extent of deformation depends on the member shielding by affected radiation barriers. So radiation barrier could be your intermittent paints, it could be your boarding all around your members. If directly exposed, what expected maximum fire temperature and duration would you get? No one knows, except you design it, not by prescription-based, but by performance-based. What about RC concrete? And the majority of the people in the room, they're all happy with their reinforced concrete design in terms of fire, but then, again, 3101 section 4 gives you different sizes and different thicknesses of your members, but there are ways that they could actually be engineered from first principle, and we can actually come out with a smaller size compared to what is actually in the code. And this is where you get back to your alternative design or your first principle design as a fire and structural engineer. So solid concrete members are robust in fire. So the only take home is for hollow cores, it's a bit questionable currently, all right? So there's been quite a few research on hollow cores in terms of fire, but it's still a questionable material. And one major issue we have with concrete is spalling in fire. So what happens is, during a fire, all the water content gets to dry up, and due to that, you get spalling of the concrete. Could be your columns or your beams. Examples of reinforced concrete members behavior. So large structural members and systems, columns, beam, floors, and slab. So this is a full concrete structure. Okay? It's hard for it. It depends the various elements that would determine what we're going to expect from a concrete building. And what we understand is the columns, they usually either, they expand and they also contract, or we can have either spalling of the concrete itself. And for the beams, usually we get cracks, and these cracks are being induced by the expansion of the concrete itself and also the contraction of the concrete. So once the concrete gets heated up, it loses all its water contact and it starts to crack. And once you get a little bit of crack, it propagates to the other parts of the concrete. And this is one of the floor systems, which was mentioned previously. The floor slab, although the majority of the time they perform very good, but not all the time. So, yep, for behaviors of timber, okay, the exposed surface char rate is all known. We understand that timber, we have calculations to get the char rating of a timber structure. Individual member fire resistance similar to the fire resistance of the entire member, which means for a member to fail, it's most likely the entire structure, or the entire structure is mostly dependent on individual members for a timber building. They wouldn't undergo distortion, like the steel section where it starts to sag or concrete starts to crack. For timber, it just gives up once it starts to char and gets to a rating whereby it cannot hold anymore. It just collapses, for instance, for a timber beam. So most of the times, for timber itself, we understand the behaviors of this material in fire. So individual sections, so these are for lightweight timber, which we use for our residential buildings. They may contribute to the fire load. So if you have, say for instance, a lining which is not fire rated, okay, the timber itself in the lining contributes to the fire load in that particular setup. So that's why for lightweight timber, which I use for residential, they are pretty much well known. And these are some photos from fire tests which were done, showing how these timbers actually collapsed. So this is a steel portal frame structure. Okay, it's a warehouse, and this is a concrete frame building, a concrete structure as well. Okay, and both of them, they actually collapsed in fire. So which of these structures you think has a better capacity, or basically would perform better in fire? Is it the one on the left, which is a steel frame building, or the one on the right, which is a concrete building in fire? Which one?
Is this laminated beam?
No. So the left one here is a steel portal frame building, and the right one here, it's very difficult to see, sorry. And the right one here is a concrete building. So which one do you think, a steel portal frame building or concrete building will perform better in fire? No. Concrete. All right, everyone says concrete. Well, seriously, cannot tell without knowing the fire load. All right, so if I have a, say, steel portal frame and I just have a piece of paper burning, it's fire, right? Exactly. So basically they have different fire loads, and that's where the alternative design comes into play. Once you get to know the fire load, you could get to know what temperature you're having in your building. You can get to engineer your building to perform even better. And the same question I had, if you have, a member outside the building where you don't have anything, there is nothing on the footpath. Do you still design that member to the same member, for instance, where you have, say, fuel stored inside a particular building? Exactly. That's where the alternative side comes into play. So, fire following earthquakes, okay, there's been a few places where this has happened, and it actually caused some serious issues, but the good thing is in Christchurch, we didn't have this when there was a Christchurch earthquake. But places like Japan, Kobe, I think that was in 95, there was an earthquake, and after that there was severe fire. So one of the disadvantages is some of these members which are being used to provide, say for instance, your water tank, okay, to provide water into your pipes for your sprinklers. If there's an earthquake and they all, fall, we don't have fire, we don't have, water to, actually we don't have our active system, which is the sprinklers, to actually put off the fire. So things like that usually happen, but not in every case. So that's why majority of the time people tend to, overlook things like this. But I think in the future, this is something that might come into play when you design for seismic. You have to check your after effects, okay, in case there is a fire. So these are some slides just showing a few things that happened in the past. Okay, fire following an earthquake. And like I said, what really happened was, loss of your materials to supply water to you. And also the test being done by BHP in Melbourne for a car park. So this is one of the very well-known aspect of structural fire engineering known in New Zealand currently. Say for car parks. So I think SCN has a very, very useful guide for car park design based on alternative design. So if you want to design, for instance, a car park anywhere in Auckland, you could use the document. It's really, really helpful. I haven't used it personally, but I've had a read of it. And I think I can see a few people who actually were author of the book who actually did most of the calculations in the audience. So this is a test, like I said, of a car park, trying to understand what happens in a car park, or if the car is on fire in a car park. So basically, the fire loads generated from a car park are usually higher compared to the ones where you have an enclosed building and a variety of places, and that's why this test was actually done to understand the behavior of these actual cars if you have about one or two cars in fire, and how it actually spreads to other cars when there is a fire on one car. So the lesson learned from the Caddington test, time's almost up, I'll rush through. So a Caddington fire test, I'll just give a brief understanding or a brief intro of this test. So this test was carried out in the UK. It's one of the biggest fire tests which has ever happened. And the majority of the people involved in this were structural engineers. Okay, so that's why it gave the perspective of a structural engineer on how fire behaves, okay, or how fire affects our structures. So they built an 8-story building, okay, just to test it and test different parts of that building to see how it behaves in fire. So the range of severe fire tests, 95, 96, and the final one was conducted in 2003. In all tests with unprotected beams, structural damage, and there was no collapse of the building. So this is what the building looks like. Okay, so they had sandbags which were put in the building to represent human beings or to represent the gravity loads as well. And they tested different compartments of this particular building to see how the system reacts, but not individual members. And there were so many lessons learned, and there are still lessons being learned from this actual test still today. And majority of the time, the way we know more about fire is when it happens, okay, not through tests. It's quite an expensive experiment to carry out. So this is the floor plan, and tests were carried out on the BS restraining beam test, and they had one on the frame, they had another test at the corner, had another one at another corner, and had a whole compartment tested. They had a small office, they had the end bay as well, and those were the different things that happened. So lesson learned from that: unprotected beams that are part of the structural system, like I said, they have a higher fire resistance ratings compared to so basically the test predicted a high fire ratings compared to what we currently designed for, okay, till date. The composite floors, they performed excellently well. Bare steel beam, like I said, the detailing, that's where everything lies. If the connections are well detailed, they usually perform better. So redundancy enhanced load sharing, which increases structural resistance to severe fire attack. Okay, so basically, if one member, say if you have a column in a fire cell, gives up, now you have what you call the load path or load transfer to the other members, and that way you still get a better capacity out of your entire system, not just the individual members, which we currently design for. Lesson learned 2, structures need redundancy and robustness. Fireproofing needs deformation capability. So, for instance, I see people putting intermittent paint and having a timber stored, beside your steel section. That's not gonna. I mean, I don't know what to call that, but it's something I see more often, and yeah, it's laughable. Sprinklers need to be reliable. So, if you have a seismic event and you lose your water, you don't have the sprinklers there. Also, the egress system needs redundancy. Transfer system needs special consideration. So if you have a transfer beam, it needs a very special consideration. And lesson learned 2, once a moderate high fire load reaches full development, it is likely to spread significantly. Okay, so many things happen, so many buildings where we've seen this happen. Few of them were on the news recently. And structural damage from a fully developed fire is actually extensive, okay? It spreads very fast. The way fire spreads, we've seen it in so many buildings. You see that you have, bad cladding or whatever, it actually gets the fire spread quickly. A well-designed and detailed steel frame with composite floor is actually one of the best ways to design for fire. So composite members, they actually perform very good in fire. And that's it for me today. Thanks for listening.